Hello and welcome to our design consultation for SkyComm from Study Group Ashkin on advanced applications of photovoltaic power. Photovoltaic technology, commonly known as solar panels, has shown great potential in the renewable energy field. Over the years, significant advancements have led to the development of organic solar cells, quantum dot solar cells, and multi-junction solar cells. Among these, multi-junction solar cells stand out for their ability to absorb a broader range of the solar spectrum using multiple semiconductor materials, achieving higher efficiencies. As a result, they are widely used in communication satellites. NASA's Glenn Research Center has developed a high-efficiency multi-junction solar cell using a thin selenium interlayer for wafer bonding. This innovation offers high efficiency, low cost, ease of manufacturing, durability, and environmental effects, making it ideal for satellite applications. Building on these advancements, the next section will explore SkyComm's business model and system design requirements for integrating this technology into its satellite network. SkyComm operates across two innovative verticals: satellite communications and clean energy solutions. Its flagship product, Sky Commander, is a cutting-edge satellite-on-the-move terminal offering full duplex broadband connectivity via Ka-band satellites, even in extreme conditions. Combining advanced mechanical tracking, phased array technology, and real-time North American Aerospace Defense Command data, it ensures reliable, high-speed connections for civil and military applications. Additionally, SkyComm Power develops solar and hydrogen energy hubs at airports, sharing clean energy with local communities. SkyComm Connect powers voice-over internet protocol services in regions like the DC and Baltimore area, using renewable energy, emphasizing sustainability. Backed by the Angel Group, SkyComm invests heavily in research and development, focusing on low Earth orbit ready satellites and clean energy partnerships. This dual focus on connectivity and sustainability positions SkyComm as a leader in both telecommunications and green innovation. The on-satellite photovoltaic system must meet several critical requirements. As the most essential component of all satellite systems, often regarded as a lifeline by Yakub et al., reliability is a primary consideration. Given the constraints on satellite size and weight, the photovoltaic system should also be designed within strict limits. However, reducing its size can significantly increase costs, which must be carefully considered during development. Moreover, space missions demand substantial energy, as illustrated in the table on the right. Therefore, optimizing energy efficiency and generation capacity is crucial. Additionally, environmental factors such as extreme temperatures, fluctuations, and radiation exposure can degrade system performance and must be addressed in the design. Other challenges, including vibrations during launch, also require consideration to ensure the system remains functional throughout its mission. Based on those requirements, a photovoltaic system is customized for SkyComm. In our small satellite power system, we prioritize simplicity, reliability, and efficiency, while maintaining a lightweight and cost-effective design suitable for a large-scale satellite fleet like SkyComm. At the heart of the power generation system are the triple-junction gallium arsenide solar panels, chosen for their high efficiency, radiation resistance, and long operational lifespan in space. These panels feed power directly into the system through a blocking diode, preventing reverse current flow and ensuring optimal power delivery. For power regulation, we use a direct energy transfer architecture, or DET, which offers a simple and robust method to distribute power without the added complexity of maximum power point tracking. While MPPT is more efficient in some cases, direct energy transfer was chosen as it eliminates the need for additional converts, reducing math, cost, and failure points, essential for scaling a large satellite fleet. The decentralized power architecture, or DEPA, then distributes power efficiently to the onboard subsystems through multiple isolated converters. This approach allows for a dedicated point-of-load regulation, ensuring that each subsystem receives correct voltage and power levels. This method improves redundancy and system modularity. DEPA is a better choice for our application as it has no single point of failure, as each subsystem has its own converter, meaning a failure only affects the individual subsystem. Deeper also allows for different voltage levels per subsystem without the need for centralized intermediate bus voltage, making it ideal for scaling and modifying. For energy storage, we integrate lithium polymer batteries, which provide high energy density while being lightweight and space efficient. These batteries act as a backup power source during eclipse periods when the solar energy is unavailable. To prevent unnecessary discharge, a power switch using MOSFETs is implemented, ensuring that batteries only supply power when needed. DET provides efficient energy management, Deeper provides flexible power distribution, and LiPo batteries provide reliable energy storage, striking a balance between performance, simplicity, and cost effectiveness. Our design is scalable for mass production and ensures that each satellite in the SkyComm fleet operates reliably and efficiently. First of all, let's take an in-depth look at its core technical highlights. The core of this battery consists of 3 layers of structures like photon hunters. The top layer, indium gallium phosphate, with a bandgap of 1.85 electron volts, is like an efficient Venus flytrap, specifically capturing ultraviolet and visible light. The middle layer, gallium arsenide, with a bandgap of 1.42 electron volts, is like a precise sniper, capable of firmly locking onto near-infrared light. The bottom layer, germanium, with a bandgap of 0.67 electron volts, won't even let the last wisp of infrared light slip through its palm. These three layers work closely together, enabling the battery to achieve an efficiency as high as 39%, which is twice that of traditional silicon panels. It's worth mentioning that NASA has achieved an excellent performance on Mars rovers. Next, there's a hidden secret weapon inside the battery, namely the quantum tunneling junction. Please look at this energy band diagram. These highly doped P++ and N++ layers are like building a zero resistance highway for electrons. The conduction band of indium gallium phosphate is 0.15 electron volts higher than that of gallium arsenide, which forms an electron barrier, effectively preventing electrons from wandering off. And the valence band of germanium is perfectly aligned with that of gallium arsenide, allowing holes to reach the bottom layer unimpeded all the way. The final result is to achieve zero voltage loss and extract energy down to the last joule. The system's implementation faces real-world challenges, such as collision avoidance maneuvers, which mega constellations like Starlink perform regularly, as well as communication security and regulatory permissions. However, the biggest real-world challenge for our satellite design is a harsh space environment. Satellites are exposed to extreme temperature fluctuations, ranging from 20 Celsius to minus 100 Celsius. These fluctuations can lead to thermal runaway, material stress, and reduced lifespan. Additionally, the temperature variations can affect inter-cell and inter-module connections, and ultimately the operating lifespan of the system. Radiation exposure further degrades solar cell performance, affecting cover slide transmittance, adhesive integrity, and semiconductor efficiency. While cover slides provide protection, long-term radiation exposure still lowers energy efficiency and power output. Another important supply challenge is supply chain constraints. Our 3-junction germanium gallium arsenide and indium gallium phosphate multi-junction solar cells are subject to export restrictions, such as the export control classifications numbers under the US Export Administration regulations. This limits access, scalability, and cost efficiency. To address extreme temperature fluctuations, we integrate active thermal control systems with redundant heaters and radiators. While this adds weight, it stabilizes the photovoltaic efficiency and prevents material fatigue, critical for mission longevity. For radiation degradation, we employ radiation-hardened cover slides and redundant cell arrays. This slightly reduces power density but ensures consistent performance over the satellite's lifespan. To mitigate export restrictions of multi-junction cells, we partner with dual-use technology suppliers under the US Export Administration regulations exemptions, accepting marginally higher costs to maintain scalability. Finally, we balance redundancy and weight by employing the modular decentralized power architecture, or DEPA. DEPA's isolated converters add complexity but eliminate single point failures. While gallium nitride-based DC-DC converters increase upfront costs, their efficiency offsets long-term energy losses. Pause here to have a look at our references. Pause here to have a look at our second slide of references.